section 14.8 is about a technique called Lagrange multipliers. That's a technique for finding constrained maxes and mins. And so there are two cases that we're going to see. Case 1, the function to be optimized is going to be a function of two variables. So we would have z equals a function of x and y. Okay. The constraint then would be that g of xy, another function also of two variables, has to be some fixed number. In other words, xy must lie on this level curve for g. So what that does is it restricts the domain. It says we're not trying to maximize this function on its natural domain. We're going to only look at points that lie on this level curve. We're going to restrict the function to this level curve, and then when we do that, we'll try to find the max and the min. Okay. Obviously, if this curve is closed and bounded, and my function is continuous, then the extreme value theorem will kick in, and we will be ensured that there is a max and min. If my level curve is not closed and bounded, and very often they aren't, then a max or a min may or may not exist. Okay. So this is a technique for finding maxes and mins if they exist. It's not a theorem about guaranteeing that they exist. Case 2 would be if we have a function of three variables. So if we have w, I'm going to recycle the name f, so w is f of x, y, and z. Okay. The constraint then, we would have, I'm going to again recycle the name g, so g of x, y, z would have to equal k. We would have another function also of three variables, so that we're restricting ourselves essentially to saying x, y, and z must lie on this level surface. For g. Okay. So we're not going to work on the natural domain of f. We're going to restrict the domain subject to this constraint. Points have to lie on this level surface. Again, if that level surface happens to be closed and bounded, and my function is continuous, the extreme value theorem will guarantee that there's a max and a min. If not, the max and min may or may not exist, but this technique will help me find them if they do. Okay, fabulous. Okay, now why might we want to do this? Well, we actually ended the last section with an example of something like this. We were trying to maximize volume. We had volume was x, y, z. That's a function of three variables. Our constraint was the surface area. The surface area, which was also a function of three variables, it was 2xy plus 2yz plus 2xz, that had to be fixed at 64. Okay. So this idea of I'm going to have a function and I'm going to restrict the domain to being on some level surface may sound very abstract mathematically, but very often that comes from a realistic constraint. I want to maximize the volume, but I have to have at least this much surface area. Similar question might be I want to minimize the surface area, but I have to have a certain amount of volume. I'm in the soda industry and I'm going to manufacture cans that are going to hold a certain amount of volume, a certain amount of soda, because nobody's going to want to buy this much soda. Nobody's going to want to buy this much soda. I'm going to find a reasonable amount. I'm going to find cans that contain that volume, but I want to try to minimize the surface area because I got to pay for the materials that I use to manufacture those containers. Okay, so these constraints will in practice very often have physical restrictions. The important thing from a mathematical standpoint is that the function that I'm trying to optimize, either maximize or minimize, and the constraint function have the same number of variables. So that what the constraint does is it forces me to restrict the domain from the natural domain of the function to just points that satisfy that constraint. Geometrically, for a function of two variables, that means points on a level curve. Geometrically, for functions of three variables, that means points on a level surface. Okay, so that's the sort of problem that we're addressing. In the next video, we're going to take a look at an example to try to sort of a motivating example to try to understand the theory, and then I'll actually give you the theory of how Lagrange multipliers work. So we got a ways to go.